So today we are going to continue the discussion on computational learning theory. Just a quick recap. On Monday, we went through two simple scenarios of learning theory. One is called pack learning. The other is known as the agnostic learning, right? So in the pack learning framework, we begin with a finite hypothesis space, and we also assume that the target function is within the space. Okay, so we use concepts like version space and epsilon, just the version space to actually in here it's not using version space because the hypothesis is in the space. Therefore, it's going to able to produce a hypothesis that has a zero error on the training data, right? And then we proved a theorem which says that the probability of having at least one trained hypothesis that has a zero error on training, but still have a true error greater than epsilon is going to be very small, right? The bound is defined by the size of the hypothesis space and also, some exponential that is negative to the number of samples. So the intuition here is that if you have a more and more sample, making m's bigger and bigger, then this probability of having such a bad hypothesis will be very small, right? And conversely, you can confidently argue that if you have a hypothesis that has a zero error on training, then it is very likely to be having a very low true error. And according to that, we can actually start to characterize or estimate roughly how many examples is needed to reach a small error with a high probability, okay? Then the second scenario is a slightly more complicated where your C is not in H. And in here, we're going to use a concept called version space to basically, capture, some additional, properties. In fact, I was confused. The version space actually does include, actually apply to pack where the hypothesis commit zero error. In here, you are going to basically assume that you are going to do empirical risk minimization, in which on the training data, you get the best hypothesis you can have, which is a H hat, right? And you get a training error that is non-zero. And you want to basically now understand, how much true error you can expect from such a hypothesis. Then we use, union bounds and the Hefting inequality and proved this property, which basically says that the probability of existing a hypothesis, which has a true error that is bigger than the training error by gamma, is going to be upper bounded. It should be a smaller sign here by this number. Okay, so this number again is very intuitive. You have k, which is the size of the hypothesis space. You have the gamma, which is the probability of attainability of such a hypothesis, and the m is the number of examples. So roughly, it gives you the same message that by increasing the number of m, okay, you are reducing the probability of having a bad hypothesis, which is that this hypothesis is worse than the training error by a gamma, right? So in here you can use the m to influence both the gamma, which is the discrepancy between the training error and the true error, and also the probability of attaining a satisfactory hypothesis, right? And with that, you can now even produce a upper bound of the error, which now has two terms. One is the empirical error that you commit, on the training data, which is in here, and the other is a term which connects to the sample complexity and also the size of the hypothesis space, which is 2K in here. Okay, so that's a quick recap. I hope you can, at least down the road, remember the key ideas on this page, and then all the fancier, analysis, such as the one we're going to present today, and also a lot of the modern work, published recently on deep learning and other things, is actually, following the same vein of, ideas. Now, obviously, you see already a limitation of this analysis, in which, for both cases, we claim that H is finite, right? And obviously, this is rather unrealistic. We are only able to now deal with hypotheses which are conjunction of literals, and discrete choices and all that. Even if I want to fit a model which is like y equals to a times x plus b, right? And this is already producing you, basically it is a line, right? Dividing, a two-dimensional space. And in a two-dimensional space, how many lines you can draw? Or infinite. Therefore, this analysis doesn't apply to the analysis of even, a decision, a boundary defined by a straight line. Right? So then what do we do? We're going to now, explore another notion of the complexity of the H. Right? So the size of the H, the number of hypotheses exist in the space of H, is meant to describe the complexity of it, how rich this whole space is. If you can count it, then, or if it's finite, you can give a number. But what if it is not countable or infinite? Right. So here we're going to introduce a very, a monumental concept called the Vapnik-Chervonenkis dimension, VC dimension. That's actually the cornerstone of a modern computational learning theory analysis. It is really based on not just the specific numbers tied to a hypothesis space, such as the number of parameters and all that. It is connecting the space really toward its separation or discrimination power, in the type of examples that you are going to work with. So I'm going to be more specific about that. So what do we mean by such a power? Well, let's just maybe think aloud and see what does power usually connects to. For example, if I give you a hypothesis, which is say, let's say it is a linear decision surface. Okay, it is just parameterized by a weight vector W. Okay, and the W basically is a vector of weights. If it is one dimension, you can imagine it is a straight line. Two dimension, it's a straight line basically in a two-dimensional space with a slope and the intersection. If it is three parameters, then it is it defines now a plane in a three-dimensional space with the intersection, right? And you can imagine if I have now 1 to k dimension, then it is k minus 1 dimensional hyperplane in that space, right? So isn't this a good description of the power? Right, the higher the space, the more kind of type of data points that you can allow. For example, originally you have only data points which are described by 2 words, right? And now if your space become very big, you can classify documents which use a bag of word model in say 1 million type of words, right? Or pixels in images and that. So power obviously connects to the dimension, of the parameters. Okay. So more power, if you have more power, what's the risk? Well, typically we probably can guess that if you have a lot of parameters, such as a deep neural network, there is a very well-known notion called overfitting, you're likely to overfit the data, right? And then if you have low power, then you may be not overfitting, but you also fit the data very, very poorly. You have a lot of errors on the training data, right? So this is, again, a trade-off. So that's usually more intuitive when you are talking about dimension of the data, of the hypothesis. But we also have cases where high dimension does not necessarily mean a greater chance to overfit, and the low dimension or low number of parameters does not necessarily mean that it is weak. Okay, so let's maybe take a different view about how to characterize the amount of power. So here I'm going to introduce a very interesting concept called shattering. Okay, so here's a definition of the shattering. It starts with a data set of M examples. And then let's define the game. I give you I'm given M data points, okay? And then I am going to provide a hypothesis space. Say it's a line, or it's a plane, or it's a circle, or whatever. I'm going to name one, okay? Then you are allowed to label these endpoints arbitrarily any way you want. And you challenge me, can you use your hypothesis space to resolve all the ways that I can label the data? Okay, and if you can resolve it, like my arbitrary way of labeling M data points using your hypothesis space, but you cannot resolve it, my arbitrary way of labeling M+1 data points, then I say that your hypothesis space is shattering this data set Fs. Okay, so shattering is just basically you crush this oracle of arbitrary labeling with a predefined hypothesis space. So remember, this is a character of the capital H or calligraphic H, not a little h. Okay, you are allowed to use any little h out of that capital H to kind of defeat my labeling or to resolve my labeling, but you cannot go beyond that capital H. For example, if I say H is a line, you can use arbitrary slope and intersection, but you cannot use a circle, okay, or use a problem or something like that, other higher dimensional curves. Okay, so clear so far? Let's look at a example. In fact, you can imagine that this is a pretty interesting and challenging task, in terms of shattering a data set. Because if you are just worried about the binary label, for example, I have M data points, each one is a binary, then I have 2 to the power of M ways of labeling that, right? And your hypothesis is supposed to be powerful enough to resolve all these possible labels. So how that works? Let's take this example. So here I have an instance space of X. These are 3 data points. The X are not, they're just positioned in this way. Okay. And
Professor, can I ask a question?
yes.
Yeah, so if you're labeling, so for the shattering definition, if your labeling is arbitrary, then why, for example, like H is limited to a certain class, such as linear?
Oh, because I'm using this concept to characterize different H. If you are choosing a different H, say there are circles, like in here, I'm using ellipsoids as the H. Okay, then they may shatter, they may have different powers of shattering a data point, a data set.
Okay, but your arbitrary labeling is within that H? Or it's just any labeling possible?
Any labeling on the S. So we have a S, we have a H, right? Okay. S basically is where I can apply arbitrary label. And then my H is going to provide a way of resolving all this label. Basically, resolving means that I define a boundary, and on this side, I label data one way. On this side, I label the data another way.
Mm-hmm.
Wait for example, hopefully you will see the clear cases. Okay.
Okay,
So,
thank you.
For example, I claim that here, I can label these 3 data points in arbitrary way and allow my, for example, I can say this one is positive and this one is negative. These 2 are negative. Then isn't that this particular ellipsoid is helping to resolve that? Right? Now I change the label. I'm saying that all of the data points are negative and otherwise they are not. Then I can also draw maybe this big ellipsoid and say within this ellipsoid, they are all negative and otherwise are positive. I want you to try your experiment. You can just draw, there are 8 possible ways of labeling these 3 points. You just label all of them. You draw 8 graphs. Okay, you just put all your possible way of label. And I want you to convince yourself that by drawing positioning different ellipsoids, you can basically literally have a clean separation with no mistake that one label is inside the ellipsoid and other label are outside of it. Okay, does that help to understand the concept of shattering? So labeling is basically the complexity of the problem. And then H is providing the richness of the solution to that problem. Can I solve that problem or not? That's my is my house having the solution that solves your complex problem or not? What is the point? Yeah, so I'm just talking right now. I don't actually say how these points are positioned. Okay, that's actually another subtlety in the shattering point. It's only worry about the number of points. Okay, I basically say that because we're talking about a limiting concept, not the special instances. I'm talking about the worst case scenario. Okay, or the best case scenario that your data points are positioned, in some way. Maybe you give me 3, I position your 3 data points, and you label it arbitrarily, and then I shatter it, something like that. You just have to, yeah, Daniel is answering question. Great, thanks, Daniel. All right, so that actually helps us to now connect the hypothesis space, the complexity of that, to the complexity of the problem. And with a concrete quantity, okay, which we call the VC dimension. The VC dimension basically is the size of the largest finite subset, okay, of H that can be shattered by H. Okay, so X is of course is the instance space. It can be anywhere from empty to many examples. Right. So what is the largest subset whose arbitrary labeling can be shattered, can be resolved by members in the H. So that basically defines what is known as the VC dimension. If you have a scenario where like a arbitrary, infinite, an infinite set of, H can be shattered, then you could run into a VC dimension of infinity. Okay. Let's get another example. Okay, I have many examples. In fact, you may run into examples in your homeworks or elsewhere, but let's see how to crack this problem. So here, again, let's consider the X in a 2-dimensional space. And the concept is, again, binary labels, okay? And now I define a slightly weaker VC space, okay, which is now just a line. Okay, so this is a space. Your line can be arbitrarily oriented and having the intersection with the coordinates and so forth. And I have 3 points. Okay, and let's first look at the 3 points, oriented in this way. And here are the 8 ways of labeling all these 3 points. Okay. And you can see that I label it all positive and all negative and positive on some and negative on others and so forth. And I can always place a line somewhere, okay, to perfectly classify it. Okay. And you can also show that if you have 4 points, okay, and however you place it, it could be just the 4 points like this. It could be in any other way. As long as you allow me to arbitrarily label them, you cannot have a line to resolve it. Because, for example, I can label this as this, and this, and this, and that. You cannot resolve it with a straight line, right? So as you know, the 3 is actually carrying a notion of a maximum. It is a maximum number of points that you can resolve, okay, whose arbitrary labeling can be resolved by your line. Therefore, the VC dimension of this line is how many? The VC dimension of, okay, people answer 3, great. Okay, good. So then I think some people may be curious about this case, right? So I have now also 3 points, and one of my arbitrary label gets me to this configuration, and obviously this cannot, be resolved by a line. Don't worry. The definition of the VC dimension basically is not meant to be exhausting. It basically said that as long as you can pick one data set, okay, of size 3, whose arbitrary labeling can be shattered, then we call it the VC dimension of the hypothesis. Okay. Well, this is by definition, that's how Wapnik wants it the way, and you will see a reason down the road, because it basically gives you one way of consistently characterizing the hypothesis at the power of the hypothesis space. Okay, you may be finding other ways more appealing to you, but they may be less appealing to others. There isn't agreement. This one is agreed upon. It's very, very consistent. It basically allows all people to be able to draw the same conclusion in terms of the power of the hypothesis whenever they look at the same data set from different angles. Okay, so there is at least one set of the size D that H can shatter. Okay. All right, so that allows us to now start proving some good theorems. Okay, for example, one of the theorems says that if we consider the set of m points in our n-dimensional real space, okay, and we can choose any of the points to be the origin, then you can prove that the rest of the m points can be shattered by a oriented hyperplane if and only if the other point vectors are linearly independent of each other. So this can be proved. We are not going to prove here, but the shatter definition allows us to achieve at this definition, this property. Okay. Basically, that tells you, in a n-dimensional space, and with a hyperplane in the n-dimensional space, what is the maximum number of data points that can be shattered? Because if they have to be linearly independent of each other, you cannot make the number of points go infinite anymore. Okay, they have to be smaller than some number, which actually is m numbers. Okay, otherwise you will be able to show yourself a counterexample that one of those points must be a linear combination of the others. Okay, therefore they are not shatterable. All right, questions? Okay, there are conversations going on. People can see it. Some good questions that Daniel was able to answer. Great. All right, so that leads to a corollary, which basically says that for a hyperplane in the n-dimensional space, we can directly conclude that their base dimensions are n plus 1. Okay. Number of base dimensions are not related to this, number of data points are not. Yeah, well, these two, it's ill-defined. Number of shatterable data points, okay, is the base dimension. That's how I see it. Yeah. All right. Now let's go on and establish some intuition or maybe a deeper understanding about how this, why we use this dimension instead of, say, some more intuitive quantities like the number of parameters to characterize the power of the hypothesis space. Okay. It turns out that VC dimension is a very profound concept, which are more, I would say, robust or maybe more accurate in describing the power of the hypothesis. And again, here I will show you at least just one counterexample to hopefully argue against the desire to use the number of examples, a number of parameters as the power of the hypothesis. It turns out that there exist functions which is infinite base dimension, but only needs one parameters. Okay, so this is kind of magical, but it's a very famous example. I just copied from the original Wapnik's paper. Imagine such a function. Okay, a function f over sinusoid of alpha times x. Okay, it's basically it's a sinusoid wave with different wavelengths. Okay, and I can show you that this particular function has infinite base dimension, meaning that it can actually shatter infinite, number of data points, or if you have a particular set of data points which are infinitely many, and you can randomly or arbitrarily label them, I can resolve it for you by making a perfect predictor out of it. Okay. So that definitely says you something about the power of this function, right? This is different from another function which is just a straight line that is also one parameter, right? This little line like this obviously is more powerful than the straight line. Right? But how to show that? You cannot show that by comparing the number of parameters, right? But you can show that by comparing the number of data points you can shatter. So here is how you can convince yourself. Here's the game. You choose the number L. Okay, you basically say that I want to see whether you can shatter L points or not. Then I'm going to choose the L data points for you. I have the right to basically set up how the data points are chosen. Okay, I'm choosing data points, not the label, but the data points. And the L, the number of data points, is given by you. Okay, and I chosen to be this. Okay, 10 to the minus I, and I is 1 to L. Then you can arbitrarily label it, okay, in a binary fashion. Then I claim that I'm going to be able to give you any label using the function I just presented. Okay, by selecting the A to be of this number. Okay. So remember, the function says that it is alpha times the x to the sine. So sine of alpha times x. Yeah. Okay. And how this can equal to yi? Okay, so that's basically the question. And hopefully you can quickly show to yourself already. So let's multiply x into here. So alpha times xi equals to what? Equals to, yeah, so basically you bring the x into this equation, and the x is able to cancel this, and which is left with another term, and that is only, y minus m1 minus yi. Then you can plug in, different choices of the y, either being +1 or -1. If it's +1, then this term basically is eliminated, and then you are left with a 1 pi. If it is a -1, then this is leading to how much? Leading to 1/2, right? And that basically leads you to the other sign of the sinusoid function. So you can convince yourself after some little algebra, after the class, to show that all the y's can be recovered for each of the xi by plugging into this equation. Okay. Okay. No more question. Okay, so till now we arrived at a concept called the basic dimension, and that's going to be in the future used as a replacement of what we originally used as the hypothesis H. Okay, and then you can prove a bound of sample complexity for the agnostic learning, where on your right-hand side, the term corresponding to the size of the model space is now replaced by a term that is linear to the basic dimension. And then there are some other constant term connected to the errors and so forth. So these look similar to this. They are not identical, okay? And that's because there are other assumptions, other mathematical conditions to be brought into. But the key part is that they are roughly telling the same story, that there is a linear dependency between the basic dimension and also the sample complexity, of a particular problem. Okay.
Correct. There's a question in the chat. Someone is saying, does the indicator function make numbers 1 and negative numbers -1?
Does that indicator function makes it's kind of a positive and negative? Well, I don't want to go into that, because you can calculate it. I don't think it's a little bit more subtle. If I want to spend time, you can see that it tells you a little bit about how far you are away from the zeroth line, and also how far you are from here. But maybe we should dive into the details after the class, because these are very, very technical algebraic details. Okay, yeah. Okay, so now we are able to deal with the problem of having hypothesis space that is infinitely many, and still able to bound it, okay, with a finite number or some explicit number that tells you the power of the hypothesis. And then we move on. Let's see how we can use this to start characterizing the error. Right. So the flip side of computational learning theory, which worry about sample complexity convergence rate, is really on the side of the mistake bound, because at the end of the day, we want to do something to reduce the mistake, right? By working on leverages in our hand, such as changing samples, but also by changing the hypothesis space. Okay, these are basically two types of places that you can really make a difference. And let's see, what does the mistake bound consist of? Well, in the computational learning theory, we always learn a hypothesis using a risk minimization. We define the risk as the error measure of the hypothesis of the prediction made by the hypothesis, right? So in here, typically this error function Q, take as its argument the parameters and the examples, and then the error cost could be square loss or other loss and so forth, and the P is unknown. The distribution of the examples are unknown, right? And in practice, we don't know the distribution. Therefore, we have to replace that risk expectation by what we call the empirical risk, which we basically are going to just count on the training example, the cost, paid by those mistakes, right? And that basically points us to the way of training the W or the hypothesis, right? And this training is typically known as the empirical risk minimization. So we want to now ask, what is the differences between the empirical risk that you train from here and the true risk? So it goes back to the same question we asked last time. There is a difference between the true error and the true and the empirical error. In here, we replace the error with the risk because there may be a different way of measuring the cost of the error, just beyond just discrepancy. It could be regression function, for example, which is not a binary counts of the mistake, right? And there may be other probability-based, loss functions. But nevertheless, there is a difference between the empirical and the expectation. And let's see what are the contributors of these different sources of the discrepancy. So here I want to emphasize some of the key concepts in statistical machine learning where people want to work against to make sure that they are contained. One is a notion called consistency. Basically, it says when you are adding examples to the training program, you want to be under a condition where it leads the learning algorithm to converge to a true kind of a hypothesis, if such hypothesis exists. So there's a guaranteed generalization that if you have infinite examples, hopefully you are going to close the gap between the empirical risk and the true error and the true risk infinitely. That's the wishful thinking. It may not be always the case, but that's what you want. And the other, of course, is the speed of achieving that, right? So how much you gain by adding more examples and how fast you can converge, right? And the third one is that there are many cases where you cannot close the gap just because the nature label the data in such a way that is beyond your hypothesis space, right? And then how can you make sure that you choose within your available hypothesis space something that generalizes well and with a bound that you can control the capacity of generalizability, right? And of course, the last one is the strategy for good learning, in terms of the algorithmic designs, of learning rates and algorithms and so forth. Right? So let's look at each of these issues one by one under the guidance of the computational learning theory. So my point is that by studying the theory of computational learning, you actually could have less ad hoc and heuristic kind of design and choices and practices in improving on all these dimensions. So consistency is a intrinsic concept, with the hypothesis space that I'm going to use, to learn a particular hypothesis. It basically says that a learning process is consistent if the model error measured on the new data set, which are coming from the same distribution as the training set, will basically be converging, okay, to 0. It will be basically the same as the error you are going to make on the training examples. There's no gap. So empirically, you can see the graph like this. This graph gives you a particular kind of a behavior where you start with a few training examples, okay, and it began with 0 error. And you can imagine the problem is very simple at the beginning, but when you have more and more examples, your labeling becomes more and more noisy. Your training error start to increase, right? But hopefully when you train more and more, your testing error or your true error, assuming they are coming from the data under the same distribution, will be reducing. And at the end, they hopefully are, meeting in the middle. Okay, there is no gap between them. So this is basically a consistent learning. Okay. But there are other scenarios where you still have the training error increase, but the true error decrease, but fail to get very close to the true error, to the training error. And that's a sign of inconsistency, meaning that there is something wrong with your choice of the age, which does not allow basically you to consistently work on the testing data. Then you probably should consider replacing the age with a new age. So in the Wapnik's theorem, there are some guidelines about where you could expect the phenomenon of consistency to happen. It's not a guarantee, but at least you can rule out situations where you never should expect the outcome is consistent. Okay, so here is the first question: under which condition a learning model will be consistent? Well, then here the answer gives you a necessary condition and a sufficient condition. It is consistent if and only if the function h, that defines the model, comes from a family of functions which has a finite width dimension. Okay, so this is a very, very important thing. Your width dimension help to characterize the capacity of the hypothesis, and only when it is finite, then you can expect that a model learned from this h can be consistent. Okay. But of course, a finite width does not guarantee that you can have a consistency, of the arbitrary model inside that. Okay, it's a necessary condition. You can pick a h in such a thing, and it is the only way to build a model that guarantees the consistency. We need to train it, on data. Okay. The second one is the convergence speed. Basically, it tells you, even though you have a consistency guarantee, which is more about a asymptotic behavior. It means that you will eventually consistent if you train on and on, and hopefully get the training the training error and the testing error meet somewhere. But you don't want that to happen too slowly, right? So how fast and how rewarding it can be when you add more and more examples, hopefully not infinite. So here the convergence speed can be characterized by a ratio between the dimension of the width dimension of the model and also the size of the examples. Okay, basically it says that the differences between the true error and the training error will be no greater than the limit that only depends on this guy. Okay, So this is another very insightful kind of observation that given a model, you should roughly expect the convergence rate to happen as a function of the dimension versus the data. Okay. And this is a very, very interesting theorem, which is also known as the Kolmogorov-Smirnov way, because it is not depending on the data distributions. It is only, a property of the hypothesis space itself, not about the data. Okay. Okay. So now let's look into how this help us to analyze, the error bounds. Okay. So it can be proven that the error bounds, okay, between the empirical error and the true error will be now upper bounded by a big O of this term, okay, which is d over m times the log of m over d, and then another term depending on the data sample complexity. Okay, and you can rewrite it and now start to expose the two sources of your true error. One comes from the empirical error, and the other comes from a complexity term that is, a property of the training example and also the property of the hypothesis space. Okay, so this is a little bit different from what we see before in the agnostic learning scenario with a finite hypothesis space, where you basically have a 2K in here. Okay, in here you can explicitly see that the base dimension is going to be linearly interacting with the data examples, and then control the rate of convergence.
Eric, there's two questions in chat referring to the previous slides.
Mm-hmm. Let me see. Does it mean that even if H is inconsistent, it can also converge? Yeah, data is inconsistent. Let me see. It also converge. Yeah, the first question: if my capital H is inconsistent, meaning that it may not close the gap, it can still converge. That's possible. There is a capacity issue because you have a finite base dimension. Therefore, they cannot just keep improving, on the data points in terms of training errors. It will stay at a particular error rate. Okay. Okay. The second question is that I'm confused as to how the previous slides relates to the convergence speed. Doesn't it just talk about the limit of differences between the errors? Not sure what the question is about. The consistency and also the speed are talking about two different but related things, right? Consistency is more about the asymptotic behavior, that at the infinite horizon, what you are going to see in terms of the true error of your outcome versus the training error. Right? It basically means that what's the ultimate capacity you are going to achieve. But the learning rate is a more pragmatic matter. It means that how fast your error can drop, as a function of the basic dimension and also the sample complexity. Right? One is about the attainability or existence of attainability. The other is how fast you're going to attain that.
Yeah, my question is mainly like, so this talks about the difference is no greater than a limit, but like, I'm not really sure how the speed fits into the slide. Like, if the difference is no greater than some limit, then I mean, I get that, but how does that affect the convergence speed?
How does that affect the convergence? It's not affecting. the one affecting the speed is the size of the gap as a function of the model complexity and the data points. Right, one inconsistency means that the size will disappear at the infinity, or the gap will disappear at the infinity. That's just a statement of asymptotic characterization. But the other is about how you close the gap with the operators you have in the model. So I'm not sure where is the confusion. I'm not trying to even confuse you. I'm talking about two different concepts.
No, I mean, the previous slide was just labeled with the convergence speed, so I just wasn't really sure.
This one? Yeah. Well, maybe this is just a terminology confusion. This guy sometimes is called convergence speed.
Oh, okay.
Okay, but that doesn't matter. Yeah, it's confusing because sometimes you may think speed is a time concept, that how soon in hour or in a day I converge. Yeah, so here it's more of a complexity concept.
Okay, that makes sense, I think.
Okay.
Yeah. Okay.
Thanks. All right. Yeah, you can see that still, this word convergence speed appeared in here. It basically says that, what is the shape of this curve look like, in terms of its dependencies, of M and now also on D, right? And once D is put in place, you don't actually see this curve anymore. You may see a much nice behaving straight line or something to give you a better sense of speed. But anyway, this type of notions is very, very qualitative, I would say. Don't take the numbers so seriously. It really is meant to point you the direction on where you can improve, those rates and the consistency, rather than calculate in how many seconds I'm going to converge. Okay, so that's not the purpose of that. So now at least we established concept that the empirical, the risk expectation, or the true risk, is consisting of two components. One is the empirical risk. The other is called the confidence interval. Yeah, again, that's another term. The gap is sometimes called a confidence interval. Okay, and again, it is very important that the numerical value of this limit is not very important. In fact, you will see people don't use the Vapnik bounds to calculate the error because it is usually off by several orders magnitude. Okay, but the trend is very important. You kind of get a sense about when such an error will drop and when such an error will reach a minimum, as you will see in a second. So maybe it's better to use a exact example to drive the conversation rather than talk about abstract concepts. So here I have a very, very concrete example. I want to fit a function, okay, in some space using this this particular form of the empirical risk minimization, which is to minimize the square error. Okay, and then using the previous insight, you can see that this true risk, which is calculated from the distribution of data, which you don't know. Therefore, this number actually is unknown. Okay, and based on these two known terms, one is the empirical error, which is based on training examples, and the other is a confidence interval that is based on the sample size and also the width dimensions. Okay, and then typically in our training, you basically are only minimizing this part. That's why it's called the empirical risk minimization, right? But how to handle this part? Okay, because if you, for example, are choosing a hypothesis in a wrong space, which has a very, very big width dimension, then however good you do here, you will still have a very large risk in this part, right? So that basically tells you why learning theory can be useful to guide you, how to train examples. Just like we talk about, for example, how to train linear classifiers. You have points in here and you have points in here. And one way is to choose to train a straight line, but the other way is to choose a highly kind of a wigged line, which has a better power in fitting the training examples and making no error. But our intuition tells us that it's not going to be good. It's going to overfit. What does overfit mean? It actually means that you have potentially this term to be very big, right? Obviously, this line has a very, very big width dimension. It can shatter more points, right, than a straight line. So that's basically the notion we want to take into account in designing our learning algorithms. Okay, so this curve actually shows you that kind of behavior. You can see that the VC confidence, okay, is actually increase, with the VC dimension divided by the sample size. Therefore, you want to have a control over that. So that leads us to the notion of
hi, Professor. So what is VC confidence?
Yeah, these are the artifacts of Hamiltonian. You can view that as something equivalent to a confidence intervals.
Okay, thank you.
Yeah. Okay, so yeah, let me just label that. Let's do it. So that be consistent. So that leads us to the other dimension of the risk minimization, which is known as the structured risk minimization. Right? Different hypotheses actually are not equal, and if we are talking about a bias and variance trade-off, which we didn't go that deeply, but it's mentioned in our supplementary material I'm going to publish, you will see that there can be a nested set of hypotheses which give you a different scale of the bias and the variance trade-off. Maybe inside here you have just a straight line x. Maybe in here you have a second order function. Maybe in here you have a third order function and so forth, right? So each of them is a space of all possible realizations, but they have a larger and larger base dimension, and therefore they are more and more likely to be biased, right? And less variant. So at the end of the day, your structured risk minimization technique should choose a H, which is to minimize the overall bound. By choosing different H, this term will be changed, and this term also will be changed. Therefore, you want to do it in conjunction with the empirical risk minimization so that the sum of them is going to be under control. Okay. I was looking at a curve. Yeah. So this actually tells you some behaviors, right? On the one hand, you want to select a H and train them so that it reduces the empirical risk. But on the other hand, when you are choosing greater and greater model complexity, you actually are going to widen the confidence interval, okay, between the true error and the empirical error. So therefore, the best kind of total risk is a sum of these two together, and therefore your sweet spot may be somewhere in the middle, like this, that you choose both the hypothesis in its best kind of confidence interval, and also you minimize the empirical risk. So this technique is known as the empirical risk minimization. Okay. Yeah, so this is a slightly more explicit dive down of the strategy. You can basically just use this bound and try to use this dimension as a control parameter, to start controlling the bounds. Okay, and typically you are going to kind of select from smaller to big a H whose width dimension is known. Okay, and then you are going to train the best hypothesis H, inside this particular space. And then you are going to now choose a different H and try a different dimension. And then you're going to train this again. So this is a little bit difficult to operate in practice because when you plug in this number into here, it does not necessarily give you a accurate estimate of the numerical value of the error because there is a big O here that you don't know. Okay, so it only gives you the trend. You actually don't know exactly which D is the best, just by computing the error in here and plug in this term. You have to basically go through a whole sequence of H, okay, and then just train each of them, and maybe have a holdout a data set, as a cross validation data set to compute a estimation of that, okay, and then whichever gives you the best kind of holdout error will lead you to the best choice of the hypothesis space and also the H inside it. Okay, so this is something that confuses a lot of people. This equation is meant for a guidance of the strategy that you are going to choose a nested set of hypothesis space to try the hypothesis inside. It's not an equation for you to actually compute the error bound and start qualifying different hypotheses. Okay, so this is very important. Never do the following. Never do that. I'm going to train a H of hat. I'm going to basically define the sigma of that just by plug in the empirical, which I can train from the training example, and plug in a term of say a G of D and H and M, and therefore I'm going to compare this guy directly. Don't do that. It doesn't work because this particular function is highly unreliable. It gives you the trend, but not give you the numerical quantity. Okay. So in practice, what you still need to do is to use cross-validation. You're going to select hypothesis in this fashion, and then choose the best one out of it. Okay. Question: error hat H is bias or variance? It is bias. And the O is the variance, yes. Okay. All right. Now let's put the SVM, the SRM in action. How can we control basically the D? Right. I actually already mentioned one, which is an easier one, where you just are choosing the H to be a sequence of polynomial functions. For example, first order, second order, and third order, basically line, a curve, and a ball, whatever. Okay, so this basically gives you the order of the functions. But that's sometimes still maybe not enough because it is didn't give you enough kind of freedom to try additional control of the variance. So here is a method people often use to allow you even stay within the linear models, okay, and then try to control the empirical, the structural risk, because even in linear models, you actually still could run into what is known as a feature selection problem. You have a linear model of m dimensions, and then how to control the dimensionality such that they give you a trade-off between a low dimensional, low base dimensional linear model versus low bias classifier with a very small empirical error. One way is to do class validation, I just mentioned, but here there is a way to directly loop into the cost related to this dimension into the empirical risk estimation, which is achieved by something called a regularizer. You probably already learned that before already, right? So in linear regression, one thing people often do is to jointly minimize a empirical error like this, and also a regression term which controls the size of the parameters. Okay, so the Vapnik theorem says that when the value of the norm of this parameter decreases, then this dimension of that hypothesis defined by this is also decreased. Right? So we can actually leverage on this particular theorem to term basically the loss function to be directly dependent on the width dimension. Okay, and that's actually leads to the technique of support vector machine, which were covered in early lectures. If you remember, in support vector machine, it is formulated as directly minimizing the orientation parameters, subject to that they make small errors, right? And why that's actually the right thing to do? Well, it's that because the inventor Wapnik, from his insight of the VC theory, concluded that reducing the L2 norm of the W is an act of reducing the errors, reducing the empirical, the structural risk of the hypothesis. And then he was able to bring in the empirical error, by this margin constraint, so that when you are solving the constraint automation problem altogether, you suddenly are in a space where both the empirical error due to the margin and also the structure risk due to the norm of the parameters are jointly minimized. Okay, so that's kind of the beauty of that algorithm. And there are some additional benefits, offered by the SVM technique. One of the key technique is known as the kernel trick, right? Basically says that in SVM, you are able to model the hypothesis space, in what we call the RHSS, the Hilbert reproducing kernel space, by basically transforming the original data using a psi function, where in the original space where you have a nonlinear kind of a boundary, but after transformation, you are going to be, working in a linear space, right? And so then in this case, how to calculate the width dimension of SVM? Well, it's becoming very easy because this transformation, is implicitly used to transform data. Then you can basically, ask the width dimension of, the hypothesis in the transformed space, which is usually very easy to characterize, because we know that in the space of n dimension, the width dimension of a hyperplane is just n+1. We know that as a fact, right? So if you were able to now transform a originally nonlinear problem into a linear problem in some higher dimensional space, then you can directly conclude that the width dimension of the resultant hypothesis to be, the dimension of this transformed space +1, right? So that gives you, again, a very, very explicit measure about the capacity of the hypothesis using the kernel trick.
Eric, there's a quick question. Someone is saying, what is the value R on slide 35?
The value the value R on 35 when it decreases. Now, value R is just a normalization trick for the data. You can basically renormalize the data to make sure that they are all staying in a unit ball.
All right. Excellent.
Yeah. This type of things is basically not necessarily interesting for you to pay attention to, in your practical implementation. They are usually used to make the analysis, going through, by limiting the size and so forth. So, but thanks for pointing this out. Okay. Now let's just a quick reminder of where the kernel trick come from. If you know it, then hopefully it's a review. But if you forgot, just a reminder, right? So in the SVM literature, we make a pretty extensive use of the Lagrangian technique to try switching between the primal problem space and the dual data space. Right? The primal space, for example, you can build a Lagrangian by combining this loss with the weighted sum of the constraints. Right? So that's getting you the grand Lagrangian. Then by conjugate duality, you are going to attain a equivalent problem in the dual space, which looks like this, if you recall that, right? So this alpha is what? Is the Lagrangian multipliers, right, of the constraints. And we also know that due to complementary slackness, not many of the alphas are non-zero. And that it gives you the support vector kind of concept. Only a few constraints will be activated, okay? And then the other important trick is this part. It turns out that the original data training points will be only contributing to the loss function, okay, in the form of a dot product. They never exist, alone, as a data vector. They only exist when you have, a outer product, a dot product between the two vectors. Even when you learned the weights, which is a combination alpha of the data points, and when you're testing a new data, let's say I'm going to have a new Z to be tested, then this actually still results in a dot product between the two data points. Right? So that basically leads to the kernel trick. Why don't we just define a kernel function, which is directly modeling the pair of data points, and now it is a pair of data points which can undergo arbitrary transformation by phi. So we imagine that they could be a dot product in some other space, right? So therefore, this one basically becomes a K of X and Xj. And that basically allows you to virtually operate in a infinite or arbitrary kind of Euclidean, the Hilbert space, to actually still using the support vector ideas, right? So this inner product is what leads to the genesis of the kernel trick. And there are some conditions to tell you that, well, you are almost able to choose the arbitrary K function, but there are some qualifiers for the K function or the kernel function to define legitimate inner product in some higher dimensional space, which is called the Mercer condition. Right? The Mercer condition is just a way to test whether the kernel function is known as positive. Okay. But again, these are just some little maybe off-topic discussions on how to make use of the kernel trick to allow you peep into the VC dimension of a originally very complex, functions. Okay. For example, one of the most oftenly used kernel trick is called the radial-based kernels, right? Which is a exponential of xi minus xj to some window. Okay. So if I use a support vector machine with this particular kernel. Can someone tell me what is the width dimension of the model? Infinite, yes. Yeah, so if you read through a paper, you will remember that people tell you this kernel is effectively equivalent to transforming the X, by a phi, which is infinite dimensional. Therefore, the kernel trick is the VC is infinite. Then you can also see that if the VC is infinite, you may have a nightmare on the consistency guarantee, right, and so forth. So that gives you kind of a warning sign, basically. When using this kind of a very rich model, for fitting data, you are actually at a high risk of overfitting. But to be honest, people use it anyway. Very often, this learning theory is used as a guideline so that you know what you are doing. But it doesn't mean that you cannot take risk and try something that is practically working. Okay, so here is a conclusion slides which tells you the width dimension of the SVM. I think this is the key. By projecting them into a higher dimensional Euclidean space or Hilbert space, you can basically measure the width dimension in a pretty trivial fashion. And here, I reiterate the connection of your true risk, which is in here, versus the calculated VC risk that you compute from the big O encapsulated complexity function. Their trends are actually highly aligned, but their numerical values can be of orders of magnitude different. Remember, this is risk times 100, and it's still quite above that. Right? So you don't want to take those numerical numbers seriously, but the trend, where they dip to minimum and where they increase, are still aligned. Okay, I think we are at the end of the lecture. Here are some take-home message for the two learning theory lectures. First of all, you want to recognize that the sample complexity analysis can vary, depending on different learning settings, whether it is a pack learning or it is a agnostic learning, or it is about learning with a infinite hypothesis space, right? And also, you want to remember that the VC dimension is a measure of the complexity of the hypothesis space, better than counting the number of parameters. Okay. Mistake bounds of the learning is consisting of both the empirical error and also the structure error, or the VC risk, and therefore you need to do both the empirical and also the structure risk minimization in order to train a generalizable hypothesis during learning. Okay, I'm going to end here. Any additional questions? So next week we are going to have a exam. So I believe Daniel probably already announced, or maybe going to announce, that there will be some prep session for you to get familiar with the system we're going to use, right? And also there may be some reviews toward the later part of this week to help you prepare the examinations. So Daniel, you have anything to say about the exam, perhaps?
Yeah, there'll be a recitation on Friday where the TAs are going to go through a midterm from a previous semester and a final from a previous semester. And I think SAVE is also hosting a session on Saturday. You can find the details on Piazza.
Great, yeah. And the material will be everything from the starting of the semester until today, right? So make sure that you have time to review all the materials until today. Great. Okay, I will see you at the exam then. Bye-bye.